Hi folks, this is Maria, and I'm going to talk a little bit about average atomic mass, which you already started learning in class previously. So some of this will be review, and then some of this is going to be a little new. I'm going to start off with a reminder about what are isotopes. I always like to say that isotopes are just different versions of a different element. They have the same number of protons, but different numbers of neutrons. You can sort of think of it as like they're like apples, right? Where there's, we all know that there's like types of apples, there's different versions of apples, but they're all still an apple. Same sort of idea for isotopes. There's a few different ways to report isotopes, but there's two main ones that we'll use in this class, so I want to show you those. You'll notice that there's carbon-12, carbon-13, carbon-14. This is actually one of the ways to report isotopes, where you say the element name, a dash, and then the mass number. Because we're talking about isotopes, we actually know that even though the number of protons doesn't change, because the number of neutrons does change, that means the mass number also changes. So that's why carbon-12 has 6 protons, 6 neutrons, versus carbon-13 has 6 protons, 7 neutrons. The mass number is 12 because we added the protons and neutrons together. The carbon-13's mass number is 6 plus 7, so carbon-13. So that's one of the ways. Element name dash mass number. This is probably the most common way that you'll see as well when going through. The other way is using this sort of notation where you have the the symbol for the element and then the mass number on top over the number of protons. So it's mass number on top, atomic number on bottom, and it's represented similarly otherwise. You'll sometimes see this notation shown if you're, searching up different problems online. You'll see this notation where the mass number is present, but the number of protons is not. That's also a commonly accepted way of looking at isotope notation. Okay, so average atomic mass. When we're talking about the average atomic mass, it's a weighted average. I'll explain a little bit more about what that means, but it means that essentially, like when I'm looking at each isotope's mass number, depending on how many are present within the population, we're going to see a different emphasis on them in the average atomic mass. This is super important because when we're working with atoms, we're working with a population of atoms. You don't actually know which specific isotopes you're working with most of the time. At least in this class, you are not going to know which specific isotopes you're working with. You have to go a lot further up in chemistry for that to be true. The average atomic mass is always going to be reported as a decimal on your periodic table. It's most commonly going to be 2 decimal places. You may see 3 decimal places for things that are smaller, so like hydrogen and helium. Sometimes we'll have 3 decimal places. And for things that are larger, you may actually only see 1. But you're mostly seeing 2. That's the one where if you look at your periodic table, you're going to see, oh, okay, cool. It's present most of the time with 2 decimal places. Okay, you can actually also do a lot of predicting based on things that you know about either the isotopes or the average atomic mass itself. So because it's a weighted average, the average atomic mass is always going to have a mass that's much closer to the most common isotope. So if I pull back that carbon isotope figure that I showed you before, we've got carbon-12 is present at essentially 99% abundance. Carbon-13 is present at rounding 1% abundance. And so I would predict that carbon-12, because it's so much more prevalent in the population, the average atomic mass is actually going to be much closer to 12 than it is 13. When you look up on your periodic table, carbon's average atomic mass, it's 12.01. So it is in fact very, very close to carbon-12's mass number. You can do the opposite if you have the average atomic mass, but maybe you don't have the percentages of how much is present in one isotope versus another. So if I'm looking at lithium here, I know that lithium 6 is one of my isotopes, lithium 7 is the other of the isotopes. And I can see from the average atomic mass that there must be a lot more of lithium 7 present than there is lithium 6. And when I'm saying present, it's just what's naturally occurring in nature. So that's one of those things that you can do. You can do this predicting by looking at various things when going through. But how do you actually calculate it? Well, we did a little bit of this in class, but I want to lay it out for you stepwise. So that's what we're going to do. First though, I want to show you this cool image. When we're talking about lithium's average atomic mass, I mentioned before that lithium 7 must be present like a lot more. And that is in fact true. Turns out lithium 6 is closer to 7.6%, and then lithium 7 is present closer to 92%. And to give you sort of an idea of what it looks like when I'm talking about a population and with all these percentages, for each of these green dots represents lithium 7, each of these purple dots represents lithium 6. So you can see there's a lot more lithium 7 than there is lithium 6, which makes sense because when we're doing this average atomic mass, essentially taking each mass number for every single isotope that's present in my sample and averaging them all together, I would get a average atomic mass much closer to lithium 7.
Don't forget to answer the question at the end of the video. It says you have a sample of chlorine atoms containing different isotopes, and you know that the abundance of the chlorine 36 isotope is 62%, and the abundance of the chlorine 35 isotope is 38%. Do you predict the average atomic mass would be closer to 35 AMU or 36 AMU? And don't forget to write why. Thank you for watching this video.